Let's look closely at a biological membrane. To understand how a cell functions, we have to track the precise location and momentum of millions of atoms, femtosecond by femtosecond. Underneath this motion is a strict set of mechanical rules. Every lipid molecule is held together by chemical bonds, angles, and rigid dihedral structures, but the bonds are computationally cheap. This side profile shows the true complexity, the sheer density of these lipid chains packed against one another. In classical physics, every single atom exerts a force on every other atom in the system, even if they aren't physically connected. This creates a scaling problem known as big O of n squared. If you double the number of atoms in your simulation, the math required by the computer quadruples. Calculating the non-bonded interactions for a million-atom system using brute force would take decades to finish a single microsecond of simulation. To simulate life, we have to find a way to bypass this quadratic wall without violating the laws of physics. To see why these forces are so difficult to calculate, we need to look at two isolated particles in a vacuum. This graph models the van der Waals forces acting between those particles using the Lennard-Jones potential. The interaction is defined by two terms. As the particles collide, they hit a steep repulsive wall scaling at r to the negative 12th power. As they separate, they feel an attractive tail scaling at r to the negative 6th. Because that attractive force is divided by the distance to the 6th power, it converges to zero very rapidly. After a few nanometers, the atoms effectively stop interacting. Now look at the Coulomb potential, which governs electrostatic interactions between charged particles. The Coulomb force scales at r to the negative 1. This means it decays much more slowly than the van der Waals forces. This slow decay is why electrostatics are so difficult to compute. While we can safely ignore distant van der Waals forces, we cannot ignore distant charges because their influence never truly vanishes. Assigning a single point charge to the center of an atom is rarely sufficient for modeling the complexity of a real molecule. To mimic real electron density, we use multipole expansions, distributing point charges, dipoles, and quadrupoles at specific sites along the bonds. Modern simulations calculate the energy, force, and torque of these complex distributions using interaction t-tensors. T-tensors are the Cartesian spatial derivatives of the distance between particles. The zeroth derivative yields potential, the first yields the electric field, and the second yields the field gradient. These tensors allow the engine to map the exact directional vectors of forces between molecules in three-dimensional space. But at very short distances, this math breaks down. As atoms approach each other, the calculated forces begin to approach infinity. We avoid this polarization catastrophe by applying damping functions. These artificially smear the point charges into finite clouds, smoothing out the mathematical spikes. While tensors and smeared multiples resolve the local geometry, they don't solve the scaling problem for millions of distant atoms. An intuitive solution to the scaling problem is to establish a cutoff radius, telling the computer to simply ignore any atom outside a certain distance. This works for Lennard-Jones forces. Since they decay so quickly, a spherical cutoff safely ignores forces that are already essentially zero. This chart shows what happens when we apply that same cutoff to electrostatic forces. Notice the sharp vertical drop in the potential curve labeled U1. As an ion drifts across that boundary, the calculated force jumps instantaneously from a high value to zero. This sudden jump violates the conservation of energy. It injects artificial heat into the simulation, which can cause the system to explode or form unnatural liquid structures. Codes use shift and switch schemes to fix this. These equations bend the curve, forcing the potential to zero gradually at the boundary. But look at the right-hand graph. These smoothing schemes significantly alter the actual forces acting on particles compared to true Coulombic interactions. For highly charged or polar fluids like water, even these smoothed cutoffs create physical artifacts, corrupting the validity of the results. We are trapped. We cannot afford to compute infinite interactions, but truncating them destroys the physics. Molecular dynamics engines resolve this electrostatic impasse using a technique called Ewald summation. Instead of cutting the box off, we compute the interaction of an ion with all of its periodic images in an infinitely repeating grid. The primary trick involves superimposing a Gaussian cloud of opposite charge perfectly over every point charge in the system. This opposite cloud screens the point charge, causing the long-range potential to decay at the same rate as a short-range interaction. Because this screened potential decays so rapidly, we can now safely use a cutoff radius without violating physics. But we have now altered the system by adding these clouds. To fix this, we must subtract an equal and opposite background charge distribution to cancel them out. Because this background is smooth and periodic, we calculate it using wave mechanics in reciprocal space rather than tracking it atom by atom. This is where particle mesh Ewald comes in. By interpolating the scattered charges onto a uniform three-dimensional grid, the system is converted into a continuous lattice. Once the charges are on the grid, the computer can use a fast Fourier transform to solve the electrostatic fields across the entire system simultaneously. By splitting the force calculation between a short-range cutoff and a grid-based Fourier transform, particle mesh Ewald circumvents the quadratic wall, shifting the computational cost from n squared to n log n. Consider again the scale of a large biological structure like this vesicle. Every femtosecond, millions of interactions are being resolved. Under the hood of this rendering, three mathematical layers are operating in unison. First, the Leonard-Jones potential handles the rapid, short-range collisions within strict spherical cutoffs. Second, T-tensors and multipoles map the precise spatial geometry of the electron densities. Finally, the particle mesh Ewald grid utilizes Fourier transforms to calculate the infinite web of electrostatic attractions holding the structure together. Without this hierarchy of algorithms, the simulation would either freeze under its own weight or tear itself apart due to inaccurate physics. By translating physical forces into multi-layered mathematical architecture, we have built an engine capable of looking directly into the living nanoscale.